Hi, the next section is Wilcoxon signedrank test. So this is an alternative to one sample t-test, but we need much less assumption on distribution of random variables. So when normality assumption of t-test is severely violated, for example, distribution of X is very skewed or very heavy-tailed, the Wilcoxon signedrank test can be used. So this test only assumes symmetry of the distribution of observations x1 to xn under the null hypothesis, and we don't have any assumption on the alternative hypothesis. So we test whether or not x1 to xn are centered at 0. So that is null hypothesis. And alternative is any other distribution. So that means x1 to xn does not follow a distribution symmetric around 0. So this test is robust against violation of normality. So if you assume normality, we can do the test, but if assumption is violated, the result is invalid. But this test is valid under a wide range of distributions. On the other hand, this test has a lower power than one sample t-test. So that means it is harder to reject H0 even when the same data is used. So basically we have less assumptions. So that is an advantage. And the drawback is we have lower power. So basically we are on the safe side. So we don't assume normality. So we think about the general case, but conclusion is a little weak. So that is true for any test. We drop more assumptions, then the power is weaker. So it's harder to reject null hypothesis. Okay, so notation is a little complicated. So we start with an example. So think about the math PhD salary. And we think about whether these observations are centered at 79,500 or not. And typically, income distribution is not normal. Usually, the income distribution is very skewed to the right. So a few earn a lot of money, but majority of the population earn modest income. So it's not symmetric. So the normal assumption is often violated. And it's possible that we transform this by, for example, log of income, or maybe square root of income, then maybe distribution is almost around, the symmetry, and it's nearly normal. That's possible. But if we don't want to transform it, then one way is Wilcoxon signedrank test. Okay, so this test at first, and the null hypothesis. So xi minus 79,500. So first observation 55,000. So 55,000 minus 79,500. So negative 34,500. Then the same. So we subtract 79,500. So we get these numbers. And okay, so then we order these numbers with ignoring the sign, positive or negative. So you can see that the 500 is smallest if we ignore the sign, and the 14,500 is the second smallest. So 1, 2, and 3, 4, just go one by one. Okay, then after that we think about the sign. So this is negative, 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 negative. So we put just negative sign here. Okay. Then we have the 4 negative numbers and 3 positive numbers. And if these observations are symmetric around 79,500, then some of the negative ones and some of the positive ones, so those have almost the same absolute value. So the idea of the test is this. So, okay, so think about the observations with positive sign, then that is, okay, so rank 1 and rank 3 and rank 5. So 1, 3, 5. So total is 9. So we define V is equal to 9. And next we take the negative one, negative 7, negative 4, negative 2, negative 6. So the summation is 19. And we think about the smaller of V and V asterisk, then that is 9. And we test based on this. So that is the idea of the Wilcoxon rank sum test. And so V and V star, V asterisk should be similar if Xi is centered at 79,500. So in such a case, the V is around 14 and V asterisk is around 14. So remember that we have 7 observations. So always the sum of ranks is equal to 28. So that is 1 plus 2 plus 3 plus up to 7. So if we ignore a sign, that should be 28. So V and V asterisk are both 14, around 14. Probably the Xi is distributed around 79,500. But if we have some bias, 9 and 19, then we are more likely to reject the null hypothesis that Xi is centered at 79,500. Okay, so this is the idea. So we go back to the original slide, define the Wilcoxon rank sum test. So suppose that x1 to xn are IID and continuous random variables. And we want to test if X follows a distribution symmetric around mu naught. So mu naught was 79,500 in the previous slide. And with a significance level alpha. Alpha is typically 0.05 or 0.01. And signed rank of X, we say signed rank as R sub I, is defined by the rank of the absolute value of xi minus mu. So we take the difference between xi and mu naught and ignore the sign, then we rank those observations. So that is the definition of Ri. But we multiplied by 1 if positive and multiplied by -1 if negative. So V and V asterisk are defined in this way. So in the previous slide that we have seen that this was 9 and this was 19. Yeah, so in total, this is the summation. So V plus V asterisk is summation of I is equal to 1 to n. So that is the n times n plus 1 over 2. And this is constant. So that means the smaller, if the minimum of V and V asterisk is smaller, then we have larger difference between V and V asterisk. So that means we have the difference between positive side and the negative side. So data are skewed. So I mean, the data is biased to the positive side or negative side. So in such a case, that we reject null hypothesis. And then how exactly that we define p-values? We discussed this. And let V be the statistic under H0, and V is the minimum of, V is the sum of the rank for positive side, right? Positive side. So positive side, and suppose that we obtained the value V. So last time we obtained 9, right? So this is the lowercase v. Then to calculate p-value, we have to set the alternative hypothesis. And here, the alternative, at first, we think about two-sided test. And the alternative is distribution of X is not symmetric around the mu naught. Then in that case, the p-value is defined by this. The minimum of V and V asterisk is less than V. And actually, under null hypothesis, the V and V asterisk are symmetric. So those have the same distribution. So these have same distribution under H0. So we can say that the minimum of this is less than V. That means the 2 times the V is less than V. Yeah, so I think that the V should be somewhat small number. So I think that the probability of V is be 50% or smaller. Otherwise, right-hand side can be larger than 1, so it's not equal. But as long as the V is the lower side, then that's fine. Okay. So that's the null hypothesis. That's the p-value. So the idea is that the distribution of V is here. Distribution, we don't really know what distribution it has. It's discrete distribution. So we have this kind of distribution of V. And if we have observed V lowercase v, then p-value is this side and also this side. So this is symmetric distribution. So I think we need one more bins. 1, 2, 3. Yeah, maybe have to make the symmetric distribution. So then for two-sided test, the p-value is defined as the sum of the shaded area, the red area. And for one-sided test, if H1 is mu is less than mu naught, then the p-value is just one side, so this side only. And if alternative hypothesis is mu is larger than mu naught, then we only have this side. So maybe we have to distinguish, so this side. And the two-sided, we take the summation. So this is the p-value. And how to make this distribution? So this distribution is the distribution of V under null hypothesis. Distribution of V under null hypothesis. And under null hypothesis, basically observations are random. So we can randomly generate the numbers, and we can calculate, we can simulate the distribution of the capital V. Okay, so for example, if we have 7 observations as previously seen, that we generate just one randomly positive and negative sign. So basically we just choose several ones to assign to the positive side. So for example, 2 and 5 and 7, then the total is 14. So we randomly select 3 observations, randomly select any number of observations, maybe 1 to 7 observations randomly. Then we simulate the V. So we continue this maybe 10,000 times. We can simulate the distribution of V. So in this way, we can calculate p-value. Often in statistical tests with complicated test scheme, we rely on simulation to calculate the distribution of test statistic. Okay, so in terms of rejection region, since we defined the p-value in the previous slide, then we define the rejection region as this. So basically, if we have distribution of V here, then we reject the both sides, both extreme. So distribution of V under null hypothesis, then, okay, so suppose distribution is like this. This should be symmetric. Then the rejection region should be determined so that total area in the rejection region is less than significance level. So this is the rejection region. So this is the rejection region, and this is also rejection region for two-sided test. So this is the area alpha over 2, and this is alpha over 2, where alpha is significance level. Yeah. So reject only if V falls in this extreme. V is very small or V is very large, then we reject. V is very small, that means the negative side, more observations. We have more observations on the negative side. If V is very large, more observations on the positive side. So mu is larger than mu naught. And one-sided case, that we have the same thing. So suppose the alternative hypothesis is mu is larger than, mu is smaller than mu naught, then we reject only if the V is smaller than some threshold. So in this case, V is small. Mu is less than mu naught. So that means the most of x minus mu naught is negative, right? So the most of that is negative. So V is small. V is the rank of the positive ones. So if we have distribution of V, that should be symmetric. We reject only for small v. So this side. And this is the okay, so area alpha. And this is the rejection region. And the alternative, if alternative is mu is larger than mu naught, the same the other way around. So if the v is larger than some threshold, then we reject. So here is the v alpha. And the other way around. So in this way that we can do the Wilcoxon, the signed rank test. So yeah, so this is the case. And for this specific case, if we have 7 observations, basically the number of observations determines the distribution of V. And if we calculate it, probability of V is less than 2 is actually smaller than 0.025 by simulation. And probability of V is less than equal to 3 is between 2.5% and 5%. And probability of V is less than 4 is more than 5%. So if two-sided test, then we reject only if this is, yeah, so if the 5% significance level and the two-sided, then we only reject if V is less than 2 or V asterisk is less than 2. V and V asterisk have the same distribution under null hypothesis because that is symmetric. We have the symmetric assumption under null hypothesis. Okay, so the rejection region is this. Minimum of V and V asterisk is less than 2. Or we can say that the V is less than 2 or V is more than 26. Yeah, so V, the range of V is 0 to 28 and the V is symmetric. V has symmetric distribution. So we can say V is larger than 2 or V is smaller than 2 or V is larger than 28. So this is also equivalent to V asterisk is larger than 26 and V asterisk is smaller than 2. Yeah, and two-sided test, we have to have this threshold. So actually the V is less than 3 is the rejection region. And the one-sided test for another one, so H1 is mu is larger than mu naught, then the rejection region is V is larger than 25. Yeah. So this is how to implement Wilcoxon signed rank test. So in the next video, we discuss how to implement it in R.